Okay, today's topic is about inductor and capacitor parallel in series circuit and their behavior within the actual circuit. Okay, I'm going to start with the series circuit. Basically, I got the setup on the schematics. I got the generator, which I'm generating 1 volt generator. Basically, just for the demo purposes, I've used a very low voltage. And then we got the capacitor, value 10 picofarad, inductor 6 microhenry. And basically this is what a circuit looks like. You got the capacitor joined to the actual inductor. Okay, now the very first thing that I have done is I applied a formula for the resonant frequency. Just to mention it, the same formula applies for series circuit, and the same formula applies for parallel circuit, except you will see where the difference comes in. Okay, so whether it's a parallel or series circuit, if we're using the same components, it will give us always the same resonant frequency, except the circuit will behave slightly different to each other. So basically in series LC circuit at resonant frequency XL, which is a reactive impedance of the inductor, and the XC, which is a reactive impedance of the capacitor, is at minimum impedance, letting maximum current flow through the circuit. So basically this becomes minimum resistance to the current flow. So the maximum current flows at a resonant frequency. And in turn, you will see over here, the impedance becomes minimum, but Ohm's law, the voltage will become the highest type of thing, because the current is the highest. So you would get a distinct sort of peak where the applied signal, let me just draw it over here, extra, where the applied voltage is, say, up to here. Okay, that is voltage, and that's F. So that is the voltage from the generator. And you can see all these portions basically are attenuated below resonant frequency and above resonant frequency. And the maximum voltage is actually at resonant frequency. But due to the resonant sort of phenomenon between the series circuit, voltage applied across the inductor and the capacitor at resonance can be much higher than the actual source voltage that you're actually applying. So you got to be very careful, especially if you're dealing with heavy sort of bigger voltages and bigger inductors, bigger capacitors, and so on. You got to be very careful, because, as I said, you can generate many magnitude higher voltages than what you're actually applying. And I have done that basically, except the figures are very minute because I'm using very low voltage that I apply. But nonetheless, mathematically you can actually see it, that the sum of these two voltages is greater than the actual 1 volt. So for a series circuit, one's got to be very, very, very careful. Okay, because it can be lethal if you're dealing with high voltages and high inductances and capacitance. Now let me connect it up to a spectrum analyzer, and then we see how it behaves on the actual spectrum analyzer. Let's see. Sorry, I'll just put the phone down. Okay, and that basically solves the problem. Okay, I have connected it up. So basically I got the generator, 1 volt, I feed into spectrum, and this is what I get. This is what I get. If you look at it very carefully, over here, it's basically 20 megahertz. which I have calculated over here, F resonant for the circuit is about 20,56 mathematically. Of course, mathematics and due to the strain inductances and capacitance and the length of the leads, it will vary. But more or less, it is very, very close by. You can see it, resonant frequency of the series circuit. And all the frequencies, because here is my zero, that's my zero. So all the frequencies below are actually attenuated. And all the frequencies above the resonant frequencies are also attenuated. Only at the resonant frequency is the highest voltage. And this is why the series, LC circuit, is called the acceptor circuits at resonant frequency. In other words, lets a full voltage go through. And it can be used in many different applications, which is beyond the scope. I'm just demoing the basic difference between the series and parallel sort of circuit. So that is basically the series circuit, and you could see it very clear on the spectrum analyzer, which I explained already what is happening there. Let me disconnect it and then go now to the parallel circuit. Now, parallel circuit basically consists out of the inductor and the capacitor, okay, connected to each other, parallel, and then you get the generator connected across them. And this is what it looks like basically. Okay, you get the inductor and a capacitor, and they're connected in parallel, and then generator connected across them, and of course, put in series with the spectrum, so we can measure. And I haven't changed the settings on the spectrum, and still the same generator. Now, the parallel circuit exhibits, again, we apply the same resonant frequency formula, and we again get 20 because we're using the same components, 6 microhenry and 10 picofarad. So basically, I still get the 20,56 mathematically. Okay, except right now we said for the series circuit, the impedance was at its minimum. Right now, for a parallel circuit, the impedance is at its maximum. Okay, and you can actually see, XL becomes equal to XC, and when they become equal, sort of in values, but they're 180 degrees out of phase, creating high impedance with minimum current going through, the actual, trying to appear over here, type of thing. So it's a minimum current that actually flows, okay? And with the minimum minimum current going through parallel circuit at resonant frequency, you get basically a minimum voltage, and you will see all the frequency above resonant frequency are let go through, because remember what I drew on that other series circuit, this is from the generator. So this is basically voltage from the generator, and this is frequency domain, and the generator is still generating exactly the same 1 volt. So once you apply and you connect the inductor and whatever, you can see all the frequencies above resonance are basically higher. And the only frequencies attenuated are at resonant frequency. Of course, there is a bit of a slope. It's not a definite sort of slope. And then all the frequencies above are basically let through. And this is why the parallel circuit, LC circuit, they call it rejector at resonant frequency. In other words, rejects, attenuates the signal at that particular sort of resonant frequency. Now, okay, let's again connect up this LC circuit. Again, I'm just going to use let me just put okay, there we go. All right, now let me just connect and voila, look at it over there. Okay, you can see we are again at 20 megahertz, which I explained that resonant formulas applies to series, to parallel, or to series, and it's the same resonant frequency, 20,56, 20,56 for the parallel circuit. So right now we're getting except at the series circuit, if you remember well, or you can rewind the video, you will see that because here is the maximum signal, here is the signal from the generator. You can see all the frequencies above the resonant frequency are basically let through. Okay, let me just increase top of 10. And you can see all the frequencies from 0 to 20 megahertz, of course, with the slope, because you won't get, as I explained, definite sort of cutoff. Okay, they lets them through, but it attenuates at its maximum the applied signal. It's missing over here. It's attenuated. It's many times smaller than what the 1 volt is actually applied from a generator. And then above the resonant frequency, again, we got a signal going through. And this is why I said it's called the rejector at resonant frequency. So that's basically, the long and the short, of the series circuit and the parallel circuit, if you look at it. Series circuit, parallel circuit. So I hope in the short time that I have got in making this video, not to make it too long, I sort of captured the essence of series circuit, of the capacitor inductor, and parallel sort of connection of the capacitor and inductor. And if there's any questions, you're welcome to direct it to me, and I'll be too happy to answer. On that note, I say thank you for watching Batos LC parallel and series circuits explained in a simplistic manner. Thank you.